Okay, welcome everyone to my continuation of what is algebra. Well, you can read what today's topic actually is, but secretly, I would like to explain why finite fields are easy. So when I first came across finite fields myself, I found them a bit puzzling and certainly much more complicated than a field, something like Q, the rational numbers, which I usually worked uh, over in the series of algebra. But actually, finite fields are pretty simple, and that's what I'm going to explain. Or at least they are simple from a certain perspective. So in particular, their Galois groups are extremely simple, which will be the main statement for today. And then factoring polynomials should be reasonably easy because a Galois group is related to factorizations of polynomials and finding roots and so on. And that's also the case. There's a slight catch, but well, it's not so bad. Um, so as I said, the main goal for today will be to explain why finite fields are easy. And the main player will be the Frobenius endomorphism, the Frobenius automorphism, or the Frobenius homomorphism, or just the Frobenius. Comes under various names. So the Frobenius, which we will see in a second. And it's based on a very easy observation, which is the starting point for today's video. So the observation is known under the funny name freshman's dream. So you think about a freshman, and the freshman wants to do a calculation, and yeah, well, let's say it's something like x plus y to the q. You will see why I'm using q here in a second. And of course, it would be very nice, like freshmen like me would dream that this is equal to x to the q plus y to the q. Yeah. As we all know, that's not true. So let's have a look at the case q equals 2, which is illustrated here uh, using a picture that I, of course, stole. Link it to the description. But it's a very easy picture. So we have a square of length x. That's this, whatever, yellow one. Length and height x, it's just a square. You have the green one of length and height y. And of course, x plus y is just the area of the big square, right? And freshman's dream is just the sum of those two uh, squares. So we're certainly missing out quite a lot. So freshman's dream just can't be true, right? I mean, no way that this is true. It's common sense. This is just no way. You're losing quite a lot. And of course, all of you, well, probably have seen at one point the binomial theorem. So this is just a sum over the binomial coefficients n over k, and it's x to the k and y n to the n minus k. So you're missing out quite a lot. You're just taking the two extremal points of the sum formula. That's what you do. So in this case, you would miss out the, well, you have 2 over 0. That's the one you pick. In freshman's dream, you have 2 over 1, which is 2. That's the one you would drop in freshman's dream. And then you have 2 over 2 is, again, the one you would pick in freshman's dream. So in freshman's dream, you would only pick the two extremal expressions in the binomial formula. I mean, even if you don't know the binomial formula, this just can't be true. It is just too simple. If that would be true, yeah, life would be so much easier or harder. I'm not quite sure, but it's certainly not true. And then comes Forbinius and says, well, maybe not. So the observation that I'm going to show you obviously doesn't go back to Forbinius, but I just name it Forbinius because there is a Forbinius endomorphism. So let's have a look why Forbinius thought, in quotation marks, Forbinius thought that, well, actually common sense is nonsense and freshman's dream is actually true. So let's have a look. So the debate here actually is that freshman's dream works in characteristic P. Why is that? Well, I just showed you, so here's characteristic 3, P equals 3. And I just showed you that this guy behaves like the binomial coefficient, right? It's just, you just have the binomial coefficient. So this coefficient here is 3 choose 1. And this coefficient here is 3 choose 2. And in the freshman's dream, I would only take the two extremal ones. But it happens that in characteristic 3, which means you're working modulo 3, well, 3 is certainly divisible by 3, so it dies modulo 3. So this actually works. So Freshman's dream in characteristic 3 seems to work. Not quite, but it's good enough. So it works for prime powers. So as long as you write down something like x plus y to some prime power, and I usually call prime powers q, then this is really x to the q plus y to the q in characteristic p, where q is, of course, what I just said, p to some k, so some prime power. In my example here, it was just p equals 3 and k was 1. And that's a funny observation. So Freshman's dream is actually true up to the slight catch that is only true for prime powers. But still, that's pretty good because this formula is so much easier than the binomial theorem. And the binomial theorem is not hard. That's not what I'm saying. But this is ridiculously easy, right? Freshman's dream, my dream. I would like to have such a formula. It looks pretty good. And what Forbinius then says is, well, this just gives an automorphism, and that's called the Forbinius automorphism, or as I said, just the Forbinius or whatever, from the field with q elements, which I'm going to recall in a second, to itself, but given by just raising everything to the p's power. Why is that? Well, the crucial calculation you need to do in order to verify that this is an automorphism is that you need to have a plus b to the q should behave like a field automorphism. So you want it to be a to the q plus b to the q, but that's Freshman's dream. Isn't that awesome? So Forbinius just used Freshman's dream to create an automorphism of fp. And Freshman's dream is this, it's my dream, right? I want this formula to be true. It's of course not true, right? We are missing out quite a lot, but it's true in the reasonable characteristic sense. And that's pretty remarkable, right? If you would discover something like that, that's pretty remarkable. That's something I wouldn't have expected, but it's true. So you have a very, very simple binomial formula in characteristic 3, which gives you, well, not in characteristic 3, in characteristic P, which gives you an automorphism of FQ, which is pretty nice. And this automorphism is called the Forbinius. In my notation, it's this, well, sigma Q, whatever. I could have called it FQ. And Fermat's little theorem, or respectively Forbinius's little theorem, so my renaming of everything here. So this is certainly not standard. This is certainly not the standard name. I just named it Forbinius's little theorem in analogy to Fermat's little theorem. I will tell you in a second why I want this to see this in analogy to Fermat's little theorem. And Forbinius's little theorem says exactly that. The Forbinius automorphism is an isomorphism, which is kind of, well, it's, so a priori what I just showed you, of course I called it already Forbinius automorphism, which implies that I already knew that it is bijective, but what I just showed you just proves that there is a map. So Forbinius also showed that this map is a bijection, so it's an isomorphism. And why do I want to, before I go to the example, why do I want to call this Fermat's little theorem? Well, Fermat's little theorem is something like a to the p is congruent a modulo p, which is really just a smaller version of this one, because this, so that's Fermat, so this is Fermat here. This actually gives you that the Forbinius for k equals 1, so q was, remember, p to the k. For k equals 1, this actually gives the Forbinius theorem, so Forbinius. So Forbinius is a generalization of Fermat's little theorem, if you want. That's why I call it Forbinius's little theorem, whatever. Again, this is not standard nomenclature. Anyway, so let's have a look at an example. So F3. So now I'm going to recall what finite fields are, hopefully in a way that you aren't scared. Like, I was really scared about finite fields for a long time. They're really simple, so stay with me. So whenever k is 1, so finite fields are given by prime powers. Whenever k is 1, this is just z mod p, okay? So it's always just z mod p. And that's easy. I mean, that's something, it's arithmetic modulo p. That's something we can do. So that's not bad. And whenever you take a certain power, so let's say you want to compute what f p cubed is, well, then this is just the following. It's fp polynomials in fp. I'm going to make it even easier in a second. Modulo an irreducible polynomial of degree 3. So whatever. I don't know. Some irreducible polynomial of degree 3. Turns out that you can take any. Doesn't make any difference. Here in my example, for example, I take f9, so f3 squared, and I mod out by an irreducible polynomial by this funny guy here. Okay. And that sounds also not so bad. So let me try to explain how that works in the notation down here that you can see in the middle. So how the Forbinius works. So I would like to write down the Forbinius, and it's actually a pretty nice map, as you can see. In this case, as a 9 by 9 matrix. Why a 9 by 9 matrix? Well, I know it's an automorphism, so I only need one entry per row and column. And I also know that my field has 9 elements, so I need a 9 by 9 grid with one entry per row and column. And those entries will be 1 by construction because it's a field automorphism. Turns out that here's Fermat. So Fermat is this little box here that I'm going to explain in a second why this is Fermat. And then you have two different copies. Down here one, and you have one down here. And you can check that this matrix has order 3, which is kind of visibly clear because all of those small boxes have order 3, except the first one, which is just trivial anyway. Which means in this case, the Forbinius has order 3. It's an order 3 automorphism of f3 cubed. Okay, but now let me explain the notation here, because there is an even easier way, or it's of course equivalent, but there's a way how a computer would think about it. Of course, I haven't done this calculation by hand. I mean, I could have. It's a 9 by 9 matrix. I'm just very, very lazy. I really could have done that by hand. I feed it into a machine. And the machine told me that the machine thinks of this F9 as follows. So you need to create 9 elements. How can you create 9 elements? Well, the easiest way to create 9 elements, if you already know what 3 elements are, is to just take tuples of 3 elements. So AB, where A and B are elements from Z mod, what is it, F3, so Z mod 3. Right, and by construction, you have 3 times 3, so you have 9 of those. So this is a notation up here and also to the side. So this would mean Forbinius takes a 0, 0 element to the 0, 0 element. It means it takes a 2, 1 element to the 1, 2 element, for example. So the whatever, let me do another one. It takes a 1, 1 element to all the way to the 2, 0 element. Okay, this is how you should read this matrix. So very easy combinatorial description. It just says it takes an element from this indexing to an element from this indexing. So I only need to tell you what those elements actually are. And the point is, I kind of don't need to, but let me do it anyway. So a computer thinks of them as just being tuples, as I said, and it should be read as follows. 0, 0, well, 0, 0 is a bit boring. Let's do AB. The AB tuple should be A times X plus B in this description of the polynomial ring. So A times X plus B. So let me do an example. In particular, this means if you think of this as tuples, addition is just addition component-wise. Couldn't be easier. And components are elements of Z mod 3. So it's component-wise and mod 3. So addition is completely harmless here. Subtraction is, of course, also completely harmless. Multiplication is a little bit funnier because you multiply them as polynomials and then you take this relation into account. So let me try to do this actually. Yeah, before I do that, let me just say if the first entry is 0, so this is dead, then this is just an element of Z mod P. And really this little box up here is, as I said, is just Z mod P. And little Fermat tells us that Z mod P, so A to the P is congruent A mod P. tells us that this little box up here is really the identity box. Anyway, I wanted to like to do an example. Let's do maybe this one isn't too bad. 2, 0 gives us 1, 1. So what is it? Well, it's 2, 0. 2, 0 is 2x cubed, because this matrix encodes the Forbinius, so it encodes taking cubes, which is, of course, 2 cubed is 8x cubed. Okay, so the first step would be to reduce 8 modulo 3. We can do that. It's 2x cubed. And now it looks like you're stuck because this table never encodes anything of degree 3. But luckily, you have this equation, which tells you that actually x squared is minus x minus 2. And if you would now successively apply this to this equation, you will always go down in degree until you hit something that you know from this table. So I don't want to do this live now because, well, it's a live calculation. I would probably mess it up. But for a computer, of course, this is easy. And if you just sit down and do it on paper or on your iPad or whatever, it's a 2-line calculation. It's not hard. In particular, for computers, this is breakfast. So this is how I computed this matrix. And so the Forbinius is pretty harmless. It's just, you could think of it as a big matrix, which looks like a permutation matrix. And then the main statement using the Forbinius, so Forbinius' statement, Forbinius' little theorem is that this is an isomorphism. The main statement for today is that actually field extensions over finite fields are actually pretty simple. So if you have an algebraic field extension, so a finite field extension of a finite field, then this is always Galois. It's always Galois over your finite field, which is in contrast to the situation over the much more complicated field Q, where not every algebraic extension is a Galois. The Galois group is ridiculously simple. It's a cyclic group of order of the corresponding Galois extension. So it's some Z mod n, which is in stark contrast, really, really stark contrast to the situation over the rational numbers. We're going to get to there in a second. And the generator of this cyclic group is the Forbinius. So Forbinius is also the automorphism you're looking for as a generator of the Galois group. I mean, and that's just a ridiculously simple statement. It's simple, powerful. It treats all finite fields and all finite field extension of all finite fields, which are all finite fields. Anyway, and it's really, really different, as I said, from Q. So this is, of course, also completely different from Q. So let me just go to the second point, so point B here. So over a finite field, Galois extensions are always cyclic. Over Q, Galois extensions are rarely cyclic in a very, very strict sense. Namely, if you just take polynomials, the number of polynomials of degree D, at most D, that's, of course, an infinite number. So you also want to bound your coefficients. So let's say the coefficients are reasonably bounded by n in a reasonable sense. So let's say you take integer coefficients or something like that, right? Then you can bound your coefficients by n. And you take this quotient by exactly the same polynomials, but those who have Galois group as bad as it gets, as far away from being cyclic as possible, namely the symmetric group of the corresponding degree, which is really, as I said, as far away from being cyclic as it gets, right? And you would like to calculate this ratio. So how many polynomials are actually badly behaved? Badly behaved in the sense that you get a symmetric group. And it turns out that if you take the limit of this, so this is a non-trivial theorem. It's also not so hard. Link is in the description. If you take the limit n to infinity, so it goes to 1, which basically means that, well, all polynomials, or let's say it's this way: a randomly chosen polynomial with rational coefficients has Galois group, the full symmetric group, which is really morally speaking, really the opposite of what happens for finite fields, where you get a cyclic group, which is as easy as it gets. So that's why I think finite fields are much easier than Q. So their breakfast for a computer, their Galois group is as trivial as it gets. And that's pretty nice. And turns out that solving polynomial equation over finite fields is also not so hard, up to a slight catch. So one of my this is really nice. It's just a little lemma, but it's surprisingly easy and very nice. So if you ever want to check whether a polynomial has a solution in FQ, the only thing you need to do is you need to compute the greatest common divisor of P and this polynomial here, x to the q minus q. And if that is not one, then you have a solution. Now, if it's one, you don't have one. And it's just, I mean, that's easy criteria, isn't it? I mean, that's really easy to compute. Something I don't go into details because, of course, I'm running out of time, but there's also a very nice and efficient algorithm to decompose polynomials over finite fields, which is, for example, certainly included in Mathematica or Sage or whatever computer algebra program you like. So it's very useful in practice. It's fast and very good. It's a generalization of this observation here, basically. Anyway, there's a slight catch. So what I just told you doesn't imply that you can write down a nice formula for a general, whatever degree n polynomial equation over finite fields. Basically because over a finite field, you still have freshman stream, and freshman stream implies the following funny equation. The x to the q minus 1 is actually the same as x minus 1 to the q, right? That's freshman stream. In particular, there are no non-trivial roots of unity. So the roots of unity are, at least in the complex case, so this is my complex plane here. Don't look too much at the expression. So the fourth root of unity and fifth root of unity living in the complex plane. They align themselves along the regular polygons, and they're usually very useful, and they turn up everywhere if you want to write down solutions to polynomial equations. Turns out that you don't have them in characteristic P, which is really a slight catch. And again, the reason is freshman stream using this funny equality, which comes from freshman stream. Anyway, let me wrap up. So officially, this video was about Galois groups of finite fields. I hope I did a reasonable job to explain that Galois groups of finite fields are as simple as it gets. Can't get any simpler. But secretly, this video was about, well, finite fields and why I think at least they're in some sense nicer than something like a rational field. So the main reason probably why I was so scared about finite fields in the beginning was that, well, it's the usual thing, right? You see something for the first time and you find it scary, but actually it isn't. It's pretty harmless. They're pretty nice. The friendly giant, if you want. Anyway, I'm already starting waffling, so I hope you enjoyed the video, and I also hope to see you next time.